Alright, so we're doing an experiment and analyzing the data from it to figure out if momentum is conserved in a collision. So what is going to happen here is something that I think is perfectly reasonable. This is something we might actually observe if we were to measure the velocities of these balls. So if they were to collide going 2 meters per second and 1 meter per second, I think that in real life you might observe the ball on the left heading back this way at 0.99 meters per second, and you would observe the ball on the right bouncing back this way at 1.99 meters per second. So let's pretend this is an actual experiment we did in the real world, and this is what we observed. So, judging from this data, let's figure out if momentum was conserved. Alright, so the first step to do that is let's figure out the momentum of this whole two-ball system. So we have to sum up the momentum of the first ball and the second ball and find the total momentum of the system before the impact, and then do that same process again, find the overall momentum of the two-ball system after the impact. So our initial momentum, and momentum is a vector, is the mass of ball 1 times the initial velocity of ball 1 plus the mass of ball 2 times the initial velocity of ball 2. And we're just going to keep this really simple and say that the mass of both the balls is 1 kilogram. So let's put in 1 for the mass, and the velocity of ball 1 over there on the left is going right on our coordinate system. Usually right is a positive direction, so let's call that positive 2 meters per second. And then the second ball also weighs 1 kilogram, and it is going 1 meter per second, but in the other direction. Now that's important because momentum is a vector quantity. These vectors oppose each other, so one of them has to be negative. Let's call the left one negative, because left is usually the negative direction on a coordinate system. Okay, for the lack of space, I'm just going to leave that as 1, but we know it's negative 1 meters per second. And we just add those two terms together, and for our initial momentum, we get 1 times 2 is 2, plus 1 times negative 1 is negative 1, and the initial momentum of this two-ball system is therefore 1. And the units are that of mass times velocity, kilograms times meters per second. That was before the collision. Now let's check after the collision. If we get a momentum of 1 for the two-ball system after the collision, then momentum has been conserved. Let's look at the left ball. It still has a mass, and this is the final momentum we're solving for. The left ball still has a mass of 1 kilogram, and it's going 0.99 meters per second, and it's doing that to the left, so we have to call this negative 0.99 meters per second. And then since this is a system that's comprised of both the balls, we have to also add the momentum of the second ball, and its mass is 1 kilogram, and its velocity is in the right direction. That's the positive direction, so we don't have to do negative here. And let's see, what that ends up being is negative 0.99 plus 1.99. It indeed is 1. So we've found that in this collision, momentum is conserved, because the total momentum of the system was 1 before and 1 after. Did not change in the collision. Okay, now let's look at kinetic energy. Is the kinetic energy of the two balls before the collision equal to the kinetic energy of the two balls after the collision? So let's do the same thing. Let's get a total value for the kinetic energy before and compare it to a total value for the kinetic energy after. Okay, before. We have two balls. The first one has, well, first of all, the kinetic energy equation is half mv squared, which we know well. So for the whole system, we get the kinetic energy of the first ball. Its mass is 1, its velocity is 2. We'd square that velocity. And the second ball, its half mv squared ends up being half 1 times 1 squared. And kinetic energy is not a vector quantity. It doesn't matter what direction something is moving for it to have a certain kinetic energy. So we don't need to worry about negatives and positives here. So we can just plug in those positive values and let's see, add those two terms together. Half times 1 times 2 squared is half of 4. And half times 1 squared is a half. So that's the kinetic energy of the two-ball system before the collision. We have half mv squared for the ball on the left. Is half times its mass of 1 times its velocity 0.99 squared, and then we add that to the kinetic energy, the half mv squared of the second ball. There's half times its mass of 1 times its velocity squared. And when you plug that into a calculator, this is what I got. Came up with 2.47 joules. Compare that to the 2.5 that we started with, and I think that's a reasonable situation where we maintained most of the kinetic energy. We lost, what, 0.03 joules during this collision. So this is an almost entirely elastic collision. An elastic collision is where all the kinetic energy is conserved, but that's kind of like a fairy tale. It's a fictional situation. You can never have 100% of the kinetic energy conserved in a collision. To have an elastic a collision as possible, you want the things that are colliding to be pretty hard and bouncy, very bouncy, like a super bouncy ball would be. It would have very close to elastic collisions. The opposite situation might be like Play-Doh, something that's really squishy and just sticks and doesn't bounce off. When it collides with something, it's going to stop. It loses its motion, and therefore it loses its kinetic energy. So that being said, play the next video and we'll look at the squishy balls colliding.